And from, oh, and from
Apologies.
there, she then went to Lockheed Martin Space Operations for a year before starting her PhD at the University of Virginia. Following that, she did a postdoc at University of Tennessee and then one at Los Alamos National Lab. And she has been faculty at University of Tennessee since August of 2013. And her specialty focuses on looking at precision measurements of the weak interaction using neutrons. And so that's what she's going to tell us about today. So thank you very much, Nadia.
Okay, thank you, Kyle, and thank you everyone for coming. I know it's not as late for you as it is for me, but still. So yeah, today we're going to talk about neutron beta decay, or in a more playful title, the life and death of the free neutron. It's not the only research I do. I wanted to tell you a little bit more about myself. For my PhD, I did electron scattering at Jefferson Lab, and it's still part of my program, my overall program today, where I study short-range nucleon behavior and nuclear medium effects, like what happens when you put a proton, you know, if you measure what its quarks are doing, but then you put that proton in a nucleus, that behavior changes. We observe something different. So that's what I do at Jefferson Lab. But today, as Professor Leach said, I'm going to talk to you guys about fundamental neutron physics, focusing on neutron beta decay. So a little bit of history about the neutron. I assume that I'm still going to be working for at least 20 years. So very soon I'll be able to update these slides and say that the neutron is the discovery of the neutron was 100 years ago. But in 100 years ago, people didn't know about the neutron yet. So in 1920, Rutherford observed that the atomic mass differs from the atomic number. And then he did some quick math and saw that the electromagnetism is not enough to bind a group of positively charged protons. Like the electrons and the protons is just not enough. So taking those two things together, he suggested the existence of a heavy neutral particle. You're like, oh, that sounds like a neutron. It does. But what he suggested was a composite particle, something that was a tightly bound combination of an electron and a proton. So that means that if it's a bound state of two other particles, the mass of the neutron would be smaller than the sum of those other two, and you would have to provide energy in order to break it up. But that would mean, if this were true, that it would be impossible for the free neutron to spontaneously decay, you know, radioactively decay. This was not a popular idea at the time. Chadwick famously said, yes, it is of course possible to suppose that the neutron may be an elementary particle, but this view has little to recommend itself at present. He is the one that discovered the neutron. So in 12 years, I can say it's been 100 years. And a few years later, the mass of the neutron was measured well enough to be able to say that is not only does the neutron exist, but it is not a bound state of a proton and an electron. Its mass is greater than that of the proton, and this was the first suggestion of neutron decay. Okay, and this, so for the timeline, this is 1935. So of course, if the free neutron can decay, people want to measure that. And the first measurement was published in 1948. And this was done at Clinton National Laboratories. So it was known at the time. Right now, we call it Oak Ridge National Laboratories, which is about 25 minutes away from my house here. This was not a very precise measurement. They basically said that it's somewhere between 15 minutes and half an hour, basically. So it's on the lower end, but you know, this is the best they could do at the time. So what are we doing with neutrons today? We can use the neutrons to study all four fundamental forces. Neutron scattering provides us information on neutron coherent scattering length, which speaks to the strong potential. We, of course, study the weak interaction, which is what I'm going to talk about today, specifically neutron beta decay. We can study the electromagnetic force by trying, usually this is done through attempts to measure the electric dipole moment of the neutron. Yes, it is neutral, but it is composed of charged particles. So on average, it is neutral, but it must have some kind of electrodipole moment. And the reason we want to know that is that it is a window into the how the universe came to be, because if we can measure a non-zero neutron EDM, that can be related to different theories of explaining the matter-antimatter asymmetry in the universe. And finally, gravity. So I have nothing to do with the gravity experiments, but they're extremely cool. So I wanted to mention it because I think they're not, I think a lot of people don't know about this work. So I just want to briefly tell you guys a little bit about it. So the way that these experiments are done, and this is at this point, you know, not very new. This is from 2011. The technique is gravity resonance spectroscopy. So if you have, you can have neutrons whose energy is so low, we call them ultra cold neutrons, where it only takes nano electron volt potentials to confine them to you know, some sort of holder, so to say. But then what we can do is we can use those ultra cold neutrons, very low energy neutrons. We can probe the energy eigenstates in the gravity potential of the Earth. So these neutrons are so low energy that they can do total external reflection off of some materials. And, you know, there's a whole, you know, set of companies that then produce these materials. So the way that this first experiment works is that you prepare neutrons in some eigenstate, and then you let them kind of bounce along this mirror, and then you vibrate this mirror with a mechanical vibration whose frequency corresponds to the energy transition to the next eigenstate of the neutron in the gravitational potential of the Earth. So, and if the neutron gets that energy and hops up to that next energy level, you have an absorber, something that sitting at that height that absorbs the neutrons. So if this is actually working, what you would see is fewer neutrons making it through. Your transmission of neutrons would change as a function of your vibrational frequency. But that means you're literally mechanically exciting neutrons into this other energy state. And this is what the data looked like, and that's what was observed. There was, you know, transmission is pretty constant as a function of frequency, and then bam, all these neutrons are missing because they're being excited up and absorbed by something that is sitting at a different height. So this is, I find this to be a really, really cool experimental technique and result. And there's some interesting future prospects for this approach. And it's like a nice little tabletop experiment. Of course, you know, the neutron source is not a tabletop experiment, but so just a little bit about that. So the two things, hold on, is this, yeah. So the very first two big experimental neutron experiments that were done was measuring the neutron lifetime, as I mentioned earlier, which was at the time Clinton National Labs, but renamed Oak Ridge National Labs, and the neutron electric dipole moment experiment. So these are from the local papers, 1950 and 1951. And it's been 70 years, and these are still experiments that are being done today to probe these quantities. Obviously, the technology has improved, the experimental techniques have advanced, but these are still things that we don't entirely understand or have a good hold on. So, the death of the neutron are neutron beta decays. I just wanted to give you guys a reference point for some vocabulary that I'll be using. I already mentioned ultra cold neutrons whose energies are, you know, at the EV level. So this should be nano. Oh yeah, 10 to the minus 7. Yeah. So I will talk about ultra cold neutrons. These are, and they'll come up in the context of one kind of neutron lifetime measurements. And the other neutrons that are going to come up a lot are cold neutrons. So everything is referenced to a thermal neutron 25 milli-electron volts. And I always say milli because I started at JLab. So if we say MeV, we mean big M. So a lot of people mean big M. So they're not moving very fast, 2,200 meters per second. So very classical speeds, and have a corresponding wavelength of 1.8 angstroms. And as we move down this way, the neutrons just get slower and their wavelengths get longer. So this is kind of the reference point. So why do we want to study free neutron beta decay? Looking at this picture on the right, so the neutron is 2 down quarks and an up quark, and in the beta decay process, the down quark transforms into an up quark via the emission of a W minus boson, which then decays to an electron and an antineutrino. So it is the prototype for all weak decays of hadrons and leptons, right? It's, you know, the neutron is almost like the simplest atom you can have. It is the observables in free neutron beta decay are inputs to tests of the standard model, and we'll talk about how they are. And it is the neutron beta decay, and specifically the neutron lifetime, is also an input to Big Bang nucleosynthesis models. So we care about it, and a lot of other people care about it as well. So we'll start with the last one first. How is it an input to Big Bang nucleosynthesis models? So looking back in time, also we're looking back when the universe was smaller and hotter. So the time we're specifically concerned with is when nucleons are starting to exist. You can see not just free quarks flying around, but arrangements of quarks and mesons. There's 2 quarks here, as well as nucleons. And light elements are starting to form here. So between 1 second and 3 minutes. So once you have neutrons and they're free neutrons, they're going to start decaying. But at the same time, there's a competing process where neutrons and protons are trying to form light elements. So the rates between the two are going to determine the light element abundances in the early universe. And that's where knowing the lifetime of the neutron well comes in. So if you want to calculate the early element abundances, you have to know the lifetime of the neutron. So this is kind of Big Bang nucleosynthesis in one slide, and it shows the same thing that I just said in words. So if you look as a function of temperature, it's a little backwards here. The temperature gets cooler towards the right, so smaller, but that is corresponds to moving forward in time. So it kind of still makes some intuitive sense. So nucleosynthesis begins at about 10 to the 10 Kelvin, and at about 1 second, which is in the previous diagram, is where, you know, neutron lifetime starts to be interesting. We have something called weak freeze out. So there's briefly a period of equilibrium between the number of neutrons and the number of protons, where the ratio is just depends on their mass differences, which is small. And briefly, the relative amounts of light nuclei are in relative statistical equilibrium. But then the temperature continues to drop. And a few minutes later, almost all the neutrons that were available are in helium-4, and we have something called final freeze-out. And that's what's shown in this graph. So the number of protons, and this is, you know, a super log graph over here. So the number of protons is going down, but not as fast as the number of neutrons. And the numbers, the mass fraction of various light elements is coming up as they're forming. So right now, the neutron lifetime is by far the thing with the biggest uncertainty in these calculations of early element abundances. This is the thing we know the worst, which is kind of wild because neutron is such a basic fundamental particle, and it's, you think you'd know its lifetime better than you do, but we will see why we don't. So that's you know, starting from the bottom of that list and working up. Free neutron beta decay also provides a few observables that we can use to test the standard model of particle physics. So very specifically, the thing that comes in the most is what we call the Ckm matrix, which basically sorry. So there's 9 elements on there. It operates on quark states, And these values, the parameters in the Ckm matrix, we get from different kinds of experiments. And as you can see back at this picture again, in neutron beta decay, it is the down quark that transforms into an up quark. So you can, you can hypothesize that, oh, it's the of the Ckm matrix that we can measure, and it is. That's the one that we can measure in neutron beta decay. And then the standard model, this matrix is unitary, which means that we can test if it's unitary by basically squaring the entries in the first row and other rows as well, but and making sure that they add up to 1. And VUD is by far the largest element. So usually we don't even include VUB because we expect it to be very small. So there's a bunch of constants that VUD depends on, the neutron lifetime and a parameter called lambda. So the neutron lifetime enters fairly directly. And what is lambda and how do we get that from neutron beta decay? Well, we're going to talk about that as well. So what are the observables in neutron beta decay? We have our electron, so we can measure the momentum of the electron. We have the neutrino, but neutrinos are notoriously hard to detect. So while it technically exists, we don't really bother with it. We have the proton, and we have our original neutron, which may have its spin aligned in some predetermined way. So you got to keep track of the spin of the neutron. So the decay rate equation for neutron decay, so you can, there is the density, the electron energy density, the spectral lambda shows up front. And then these are the first few terms of a very long equation where the leading term is 1. And then these are what we call decay correlation parameters that can modify it. And they're have very boring names like little a, little b, big A, big B. And you can kind of see what they are. The little A1 is, I guess, one of the more straightforward ones. You can see is the correlation between the electron momentum and the neutrino momentum. Here is the dot product. So it's kind of like the opening angle between the two, as shown in this diagram. Big A, which was the parameter that's been measured the most, is the correlation between the spin of the neutron and the direction of the electron momentum. And you can see analogously what the other ones do. Little b, you're like, oh, it's only multiplying one thing. Little b is 0 in the standard model. Little b, as you can see, relates to the electron energies. So the standard model has a prediction for what the electron energy spectrum will look like in neutron beta decay. And little b is 0 if that's what we measure. And if we measure an electron energy spectrum that looks different from what we expect from the standard model, how different it is encoded in the value of little b. Okay, so now looking back at that equation, to get, we need the neutron lifetime and lambda. And lambda is ratio of some fundamental things, is the axial to vector couplings in the weak interaction. And little a and big B can all be rewritten in terms of axial and vector couplings. Those are the actual fundamental things. The neutron lifetime can be rewritten as a linear combination of these couplings, and lambda is their ratio. So if we measure both combinations, we basically know the couplings, and we know everything about neutron beta decay. And then we can determine this VUD element in our standard model quark mixing matrix. Okay, so that's what we're trying to get at, and there's different ways to get at it, and they involve very different experimental approaches with their own pros and cons. So I'm going to focus on 2 experiments going forward, which is why I highlighted little a, because it's an effort to measure little a. So I got the slide after teaching a capstone class for our undergrad seniors, because I keep referring to the standard model, and people are like, oh, does this actually appear in the standard model? I'm like, well, let me show you what appears in the standard model, okay? This is the standard model Lagrangian, and there's originally 19 parameters. There are more now because those 19 parameters, there are more than 19 now because we know that the masses of the neutrinos are not zero. And the values of these parameters are gotten from experiment. So it's of course, like, I can't make it big enough to actually see, so I put the answer on the next slide. We talk about it in terms of like the neutron lifetime and axial and vector couplings, but the information can also be represented in like that information about the mixing matrix. You can also do it via mixing angles. So those are, what we're actually measuring is some combinations of these mixing angles. And these are in the Lagrangian, okay? So since this is being recorded, you can peruse the Lagrangian later. Okay, so how do we actually test the standard model, and are we the only ones doing it, and are we any good at it? So no, neutron beta decay is not the only way to get this VUD parameter, and it's not even the most competitive one right now. So the most competitive one is 0 plus to 0 plus super loud beta decays. These are nuclear beta decays. And their uncertainties, the experimental uncertainties are the orange bars here. They have the best experimental uncertainties, but there are some corrections involved here. And this green one comes from corrections from the nuclear structure, the fact that this decay is happening in an atom. Whereas for the neutron, there is no substructure. So the reason why, one of the reasons that the neutron is so attractive as a lab for this is that the interpretation of the results is easier. But the experimental uncertainty is just not there yet. But it's about to be with this next set of experiments that I'm going to actually tell you about. They're actually, hopefully, when we do those experiments and the results come in, we're going to get so close to this that we'll actually be able to say something about VUD. Okay, so here's VUD as a function of lambda, which is that parameter that we get in looking at different correlations in beta decay, right? And 0 plus to 0 plus, they do their measurement in a very different way. And Professor Leach can probably tell you much more about that than I can, but they get a number for VUD with very good uncertainties. It's this very thin bar across the screen. To get VUD from the neutron lifetime, from neutron beta decay, you need the neutron lifetime and you need lambda. So we have to plot both on this graph and look for this intersection. And here's the particle data group number for the neutron lifetime, and here's the particle data group value for lambda. And I just included a couple of the more recent results. Well, recent at the time I made this plot. There's one more now. And you can see that it's the end, like if you look at where they intersect, yeah, it kind of touches the 0 plus to 0 plus line there. And what is this gray line? The gray line is what you need for Ckm unitarity. So basically what we're saying is like, actually the standard model is fine. VUD from 0 plus to 0 plus agrees with it. And so does neutron beta decay. But remember those theoretical corrections? So there was an update from one theory group recently. Oops, that's the wrong direction. And it moved the relative positions of these lines. So all of a sudden, we actually have a multi-sigma disagreement. And this makes this exciting, more exciting than it was before. So let's talk about now, let's delve into how we're actually doing the neutron beta decay measurements, where these numbers are coming from. So first, let's talk about a little bit about lambda. Those are little a's and big A measurements. And there's also others, but those are the two most popular ones. So I'm going to focus on the ones that are happening or have happened in the US, just so that this doesn't become a laundry list of experiments. They happen in places where we have neutron facilities. So we have that are accessible for research. So we have Oak Ridge National Lab, which has 2 neutron sources, a high flux isotope reactor, as well as the spallation neutron source. And that's where we're going to do the Nav experiment. The names tell you exactly what we're going to do. So we're going to measure little a and little b in neutron beta decay. There's the Acorn Experiment, which completed running, and it ran at the NCNR, the NIST, which is an acronym of an acronym, the National Institutes of Standards and Technology Center for Neutron Research. It's a 20 megawatt reactor outside of Washington, DC. And then we're measuring the little a correlation parameter in neutron beta decay. And then there's the UCNA/B experiment. They use the same setup at Los Alamos National Lab, where there's also a spallation neutron source to measure both the big A and big B parameters. And they actually have a result. It's on this graph. That's UCNA. But they have an upgrade path, of course. So I'm going to focus on NAB because being, normally I would say from Tennessee, but also in Tennessee right now, that's the experiment that I'm most closely involved with. So the spallation neutron source at Oak Ridge National Lab is a 1.4 megawatt neutron source. The spallation target is liquid mercury, and it's an accelerator-based source, which means that there's a proton accelerator, and at 60 hertz, bunches of protons are incident on the liquid mercury target, liberating neutrons that go into 4 pi, and then we shield, well, all kinds of other things go out in 4 pi as well. We shield for everything else, and the neutrons are transported to a series of beamlines. This is not a nuclear physics facility. This is a material science, biology, solid state facilities. All of these are dedicated instruments that do a specific kind of measurement. We are the lone nuclear physics beamline. It's lucky number 13. So this is just kind of what it looks like. Everybody kind of gets a pie slice looking down at the target, which is right here. So that's when we get to the picture, when it looks like a pie slice, that's our experimental area. So actually, that's why NAB looks like this. So this is kind of a side view. You see we have two neutron beam lines, and just for reference, just to kind of get an idea for the size of things, this is the floor. This is a hole in the floor, and the beam lines is 6 feet up. And this giant, like at the time the concrete was poured for the floor, we knew that this experiment was coming, and we needed this really, really, really tall magnet. So that's why the pit was dug. It was to be able to accommodate the magnet, and it's going to stick out through the roof. And we're going to talk about why that is. So the Nav experiment. So this is going to be the first beta decay experiment at the spallation neutron source in Tennessee. So where the neutron beam comes along, and ideally will mostly just pass through the experiment and interacting as little as possible with the apparatus. The thing, and these are cold neutrons, so remember they're like 2,000 meters per second. These are not the ultra cold neutrons. These move along. The thing we're interested in are the protons and the electrons from neutron beta decay. That's why we have this really, really big magnet. It grabs the protons and electrons and directs them to detectors, one at the top and one at the bottom. These are large area. When I say large, I mean 10 centimeters in diameter, pixelated silicon detectors. We have an asymmetric magnet. While electrons and protons can go to either detector, this design is meant to longitudinalize the momentum of the protons that are going to end up in the top detector, because for our measurement of little a, we need to measure the momentum of the protons, which means we can't, if they're not longitudinalized, then what we're measuring is some component, is just the component of the momentum of the protons. We need to longitudinalize them and make sure that by the time they get to the detector, they're perpendicular to the face of the detector. So when we stop them, we get their whole momentum. And that's why the magnet is so asymmetric. For the electrons, we detect their energy. They're highly energetic. So the electrons arrive first. The thing about detecting protons in neutron beta decay is that the endpoint energy for protons in neutron beta decay is about 750 electron volts. In these silicon detectors, they have a little oxidized dead layer on them that's like very thin, like 100 nanometers. And a proton moving through the dead layer would lose 10 kilo electron volts. Our proton doesn't have 10 kilo electron volts. It doesn't even have 1 kilo electron volt. So in order to detect it, the detector and all the associated things with it are actually biased to minus 30 kilovolts to give the protons, as they arrive near the detector, that last boost so that we can actually see it in the detector. What else do I want to say about this? These are projected uncertainties, 10 to the minus 3 on little a, and 3 to the minus 3 on little b. So we're going to detect these in coincidence, meaning that, we're going to reconstruct, we're going to make sure by time of flight reconstruction, we're going to make sure that they came from the same neutron event. Okay, this mostly exists in real life at this point. So this was designed on the of the Nav magnet. This is the beam port. It's 6 feet off the ground, like I said. And there are high voltage gauges on each end because we want to be able to bias the detectors. The colors, the Mardi Gras colors, are not an accident. We have a very active collaboration member who's from Louisiana. So it's a pretty big looking apparatus in person. The magnet is 7 meters tall, and it's not taller because the crane would hit it. Turns out the crane hit it anyway, but. So I just wanted to show you guys what the silicon detectors look like, just because my students and I have spent a long time working on them. We said that they're pixelated. The pixelation is on the back. On the front, it's one single crystal piece of silicon, but it's pixelated on the back, so you can read out each pixel separately as its own signal. The detectors need to be cold. So on the front, the single crystal silicon is actually, it's basically a mirror. Like people are like, oh, there's a pattern. No, it's reflecting the ceiling. It lives inside this copper armor, which is then cooled because we want the detectors to be cold. Because the proton signals are so small, we want to make the noise as low as possible. And for that, we make things cold. So this is the shot of UT graduate students, postdoc, and undergrads working on prototypes of the cooling system for this apparatus. They're totally working, totally not just posing for the picture. It's something that we designed and manufactured at the UT machine shop, physics machine shop. So if you have questions about it, feel free to ask, because I feel like it's really, really cool. So, okay, let's say we do NAB, and with our statistical uncertainty, we have a little a value that is competitive for VUD determination. We still need the neutron lifetime. So how do we do that? There are two main categories of experiments to do that. They're called beam experiments and bottle experiments. Sometimes the bottle experiments are also called storage experiments. And it's basically, so let's start with the bottle experiment, because I think it's more intuitively the one you would think of if somebody asked you, how would you measure the lifetime of something radioactive? You would say, well, I would get a bunch of radioactive things, see how many I had, and then check how many I had left sometime later. And that's basically how the bottle measurement works. You can find some neutrons, you start the clock, and you see how many neutrons are left later. This works fine for things whose lifetime is, reasonable, measurable. This is not a good way to measure the lifetime of plutonium, which is like 10,000 years old. But it's fine for neutrons whose lifetime is about 15 minutes. The other one is the in-beam measurement. And here we have a beam of cold neutrons that we build our experiment around. And so this kind of sounds similar to what we did for NAB, but we're trying to do something different. So we know where we pass that beam of neutrons through a fiducial volume so that we can figure out the density of neutrons in that volume. So we need to know that volume very well and our neutron fluence so we can figure out what's inside this volume. And then we also keep track of the protons that appear in that fiducial volume from neutrons that decay in flight. So d and dt, that's our protons, and we have our neutron fluence that we keep track of. And then we get the lifetime that way. So when I started working on neutron physics in the 12 years ago, this was the state of measurements, not all the way back to the beginning of time, because remember the very first measurement said it's somewhere between 15 minutes and half an hour. So if I tried to draw that, it wouldn't fit on this graph. But the ones that were had reasonable error bars at the time. And we have red squares for beam measurements and blue circles for storage or bottle measurements. And the yellow filled in bar here is the particle data group average, which included both. And you can see that they're kind of like converging on a single number. And the last one here is from 2003. And then very exciting things happen. In 2005, a Russian group published this result, which was very far away from the others and from the average, and it had very small error bars. And at the time they published it, the particle data group actually would not incorporate it into their official number because it was too far from everything else that has been published. And then a few years later, there were two, not as precise, two other numbers that were also low. So this is a problem that appeared in 2005 and wouldn't go away. And then kind of looking, but you're like, well, this is like kind of a new trend. The previous storage numbers were also high, so what happened over here? Well, they also decided to go and look back in time. One of these was retracted, and the other two were reanalyzed with updated correction methods. So now they too appeared in the new lower band of experiments. So all of a sudden, this new trend emerged where it wasn't that this one experiment produced an anomalous result. It's that the beam method consistently seems to measure a high neutron lifetime, and the storage method appears to measure a much lower neutron lifetime. So there's obviously been a couple of measurements since then to kind of make this trend very clear. And this is what it looks like today, where we basically have two running averages, and the particle data group average is, of course, much closer to this one. You can see there are a lot more storage measurements than there are beam measurements, and the burn and the U results are the same techniques, and I think some of the same apparatus even. The experiment at J-Park in Japan, they're obviously not competitive, but they're starting a program, and the approach is different enough from these two that they're just cool, and it's a placeholder for when they do have a result. So let's talk about how we do these experiments. Historical note. So going back to this, you can see that there's a lifetime point in 2005, and all of a sudden it's not here anymore. This point moved to 2012, and its error bar shrank, because what happened is, and we're going to talk about this some more, is that the largest systematic uncertainty associated with this experiment was reevaluated, and the correction reapplied and published as a new result. So it's the same number, but because of this new correction, it now sits at 2012 and has a better error bar. Okay, so going back to this plot where, we have like, a little bit of a beginning of a controversy. This is the particle data group lifetime number. What happens if I put the beam lifetime number on here? It's in yet another place altogether. So we have a lot of not quite consistent results in the neutron sector that we need to sort out. Okay. So the bottle measurement, let's start with that one because that's how it appears in the slides. So we basically put some neutrons in a bottle, and the bottle can be a material bottle, something that can externally reflect cold neutrons, ultra cold neutrons, or it can be a magnetic bottle because neutrons have magnetic moments, so they can be confined that way. You put them there for some time and then see how many neutrons are left. The difficult part here is the thing you're actually measuring is not the lifetime, it's the holding time. And neutrons can be lost in a variety of ways, not just to neutron beta decay, but depending on what kind of bottle you have, they can be absorbed in the walls, they can upscatter out of the bottle, or if it's like not a single piece of material, which it often isn't, like it's a neutron, it's pretty small, it can get lost through the walls if there's even a tiniest crack in this bottle. So whatever you measure, whatever holding time you measure, you have to correct by all these other loss processes to get the neutron lifetime. Okay, somebody raised their hand.
That was an accident, sorry.
Oh, okay.
Okay, I was excited for a question. Okay. Okay, so, and the kind of the state-of-the-art experiment that exists for this method is called UCN tau. UCN for ultra-cold neutrons and tau for the lifetime of the neutron. And they use one of the coolest traps ever designed. It's a Magneto gravitational trap. So it avoids material loss because it's a magnetic trap. It's an array of permanent magnets. And it's made into like an asymmetric shape. So like the bowl like that they build is not quite the same on both sides. And that's to address one of the systematic errors, because if it's perfectly symmetric, you can end up with neutrons that are like trapped and like they're kind of quasi-trapped, they keep, but they're not detectable. So by breaking the symmetry, you're making the neutrons, make sure that the neutrons kind of explore the whole phase space of your trap. And the way you measure the neutrons, so you load from the bottom, you fill it from the bottom, and then you let them, sit there or evolve for 10 to 15 minutes. And then you lower a dagger made of neutron absorbent material that is very quickly absorbs all the neutrons. You retract the dagger, and they've gone through several designs of this dagger, depending on what it's made of. Usually the neutrons are absorbed, and very quickly there is betas that are produced from the process that are detected. So, you collect the neutrons, retract the dagger, and look at the decay particles from the neutron capture. So the thing that they do exceptionally well, so like I said, you're not measuring a neutron lifetime, you're measuring a holding time or a storage time, and then you have to correct for all these other effects in order to recover the neutron lifetime. So here is a graph showing what they measured, the storage time, and how big the correction was to go to the neutron lifetime as a function of time. And here, and this is the UCN tau experiment. I did not forget to add the arrow. It's like the other point sits basically directly underneath it. That's how well they understand and control the neutron loss mechanisms in their experiment. The correction is basically non-existent. And if you can see in this graph, that's the PADI measurement. They also measure a very low neutron lifetime very precisely. Okay, and finally I come to the thing I work on, which is the beam approach to measuring the neutron lifetime. So here we have our beam of cold neutrons. It passes through some fiducial volume, and we constantly monitor the neutron fluence with the downstream neutron detector, and also we specifically measure the protons from neutron beta decay. And we obviously can't put a proton detector in the beam because that would interfere with the experiment. So we have to have some way of taking those protons and directing them elsewhere. So we do it with a trap. So the neutron, so what we have is a segmented electrostatic trap. And they're you know, the sections, the electrodes with holes in them, and the neutron beam just passes through. And if you recall to like 20 minutes ago, the endpoint of the proton energy is 750 electron volts. So if I put 800 volts on the ends of my traps and a neutron decays while it's in the middle of the trap, it can't get out left, right, because it sees, we call this the door in the mirror. It sees 800 volts on either end and it can't get out. And then to prevent the proton from getting out in the transverse direction, we take this whole thing and put it inside a magnet, a 4.6 Tesla magnet. So now the protons are confined in every direction. The neutrons are, of course, free to pass through to our neutron monitor. So how do we measure the protons? Well, once in a while, we open the door and let them out. And this magnet, as you can see, you know, it has a very uniform field in the region where the trap lives, but then there's a turn here. So the protons, bam, you open the door and then the protons will want to follow the magnetic field line out and out of the way of the beam. And that's where we put our proton detector. So we have the cycle where we collect, then we open the trap and we look at the protons. And this is the, we have retroactively named that 2005 experiment BL1, Beam Lifetime 1. And it had a total uncertainty of 3.4 seconds. Just for reference, all those storage measurements have an uncertainty of about 1 second. So this was a huge number. This was huge by comparison. But most of the uncertainty came from this neutron fluence monitor. And this is what Andrew Yu did as a standalone experiment. He basically came up with a cross-calibration procedure to reduce this uncertainty and also get rid of our dependence of having to look up this lithium 6 cross-section, you know, in the NDEF table. That's a whole other story. So what he was able to do, it was years and years of work, but basically he reduced the combination of these first 3 numbers. Do I have that here? No, to 0.5. So, and that's when the correction was reapplied, but luckily the neutron lifetime didn't move. So basically the number stayed the same, but the error bar got smaller. But since that was the biggest systematic uncertainty on it and it was now under control, we're like, let's do the experiment again. Because, you know, once you have something, basically they stopped taking data because it wasn't worth it, right? If your statistical uncertainty is not your limited factor, more data isn't going to help. So that's what we're doing right now. We're running an upgraded version of this experiment with some new improvements, and we were hoping to do a 1-second measurement, but we might not be able to. So the final uncertainty is not actually well known. But with the existing apparatus, we can certainly never do better than 1 second. And from the beginning of the talk, if there's 2 things we need for standard model tests, we need a measurement of lambda, which is an axial to vector coupling constant, and we need a measurement of the lifetime that's good to 0.3 or seconds or better. So we can never do that input to VUD if we don't do better on the neutron lifetime. So we're also planning to do a future measurement with a whole new upgraded apparatus that also takes advantage of some technological improvements over the last 20 years to reach to that next step. So the neutron lifetime apparatus is now installed at the National Institute of Standards and Technology in Gaithersburg, Maryland. It's once again, all of these places are not nuclear physics facilities. We're on one of the new beam lines in the, well, we're saying it's new, it's within the last 10 years. So it was an expansion of the guide hall. This is what the apparatus looks like. Remember, these protons, just like the Nav protons, also don't have enough energy to be detected. So they also have to get that 30 kilovolt kick, which means that this whole apparatus sits inside a high voltage cage, no touchy. This is what a proton looks like. So even after that acceleration, it still loses a lot of energy going through the dead layer of the detector. So 20 kilovolt signal digitized looks like this. The way we actually get the neutron lifetime is, this is, remember the trap, that the protons are trapped in a segment. So we can actually, by deciding which of the electrodes are on versus off, we can change the length of the trap. So what we do is we actually look at the proton rate normalized to our neutron fluence as a function of the length of the detector. And this slope, the slope is exactly proportional via some corrections to the neutron lifetime. So this is some early data that Jimmy Kaler, who is right here, took and analyzed. So we can come back to this if there are questions. I'm running low on time. So, so that's where we are today. But not everybody is happy to sit back and wait for new data. Some people say that, hey, maybe this is a real thing. Maybe how you measure the neutron lifetime is actually sensitive to different physics processes. Maybe you're actually measuring different things here. So in 2018, this paper appeared that proposed the dark matter interpretation of the neutron beta decay. And this disagreement. So this is my same picture as before, I just, inverted the colors. So what they're suggesting is that in addition to decaying to proton, neutron can also decay to some dark matter particle. And the bottle measurement would be sensitive to that, because to them, that's just the disappearance of neutrons. So it doesn't matter if they're decaying to protons or neutrons or dark matter, they would still register as gone neutrons. But us, who are doing the beam measurement, who are very specifically looking at what the decayed into, we would only see the proton channel, and we wouldn't be obviously sensitive to these. And they're like, and hence the discrepancy. So this was published in PRL issue 120. And literally the next month in 121, there was a paper from the neutron star community saying, no, this can't happen. So I included these in the recording. You can look these up. It's a good argument. They're basically saying, if this were true, if there was an additional decay channel for neutrons, neutron stars wouldn't be able to exist above some mass range, but they do. So, so it's a very exciting area to be working in right now. But we are planning to do another measurement. We're not just twiddling our fingers. And as you saw in my systematic error chart, we called it very boringly beam lifetime 3. So it's a bigger and more improved version of the Beal of the same technique. So we have better CAD tools than we did 15 years ago. So all the designs look nice and fancy. Here's our segmented electrode trap inside a much bigger magnet. And here's our proton detector that would see the protons. So the big thing is that this whole apparatus is bigger. What does being bigger get us? Right now, we're throwing almost all the neutrons away. We're using a 20-year-old apparatus that's built for a 7-millimeter beam, whereas the beam that's available is actually 35 millimeters. So this lets us take data faster. It lets us do way more systematic tests in a reasonable amount of time. So that also means that we can we can have a 50 times increase in the trapping volume of the protons. So if we want to take the whole beam, we need a bigger proton trap. If you get a bigger proton trap, you need a bigger magnet, you need a bigger everything. But one of the biggest improvements is going to come from proton detection. So you probably didn't catch it because I didn't leave it up on the screen long enough, but there is no improvement in proton backscattering understanding between BL1 and BL2. And not every proton that comes at the detector is detected the first time. It can be Rutherford scattered and come back out of the silicon and maybe it deposited enough energy to be seen, maybe it didn't. It'll get turned around by the magnetic field and come back, but maybe not, maybe it'll miss the detector. Or maybe it'll come back and still not deposit enough energy. Once you start splitting it up, you saw how noisy those signals are. The protons become hard to see. So there's a lot of Monte Carlos associated with understanding this process. So that's one of the things we want to do better on, and I just threw this up because this is this is the new proton detector mount design because it's the thing I'm designing. So I can talk about it if there are questions. But this is the big thing that we'll be able to do with proton backscattering. We're gonna get one of these big NAB style proton detectors. It's gonna be huge and it's gonna be pixelated, which means we're also gonna get some position information from this. And the simulations show that, so this is a simulation of what this detector would see. So now you have this kind of a cylinder of protons, right? Because the beam is not a point-like beam. So if we put it to what we think is the best position, here's the protons. They come and they make a hit pattern that's, you know, the size of the beam. But if they backscatter and they come back, the backscattered protons make a much bigger pattern because, you know, they don't have to, it doesn't all have to be at 180 degrees. And then if we translate this detector, we can vary this pattern and depending on the position where it is, if you travel too far back, you're not going to be capturing all the protons. You're going to be losing some protons. So that's what this plot is showing, backscatter missed fraction as a function of the translation. So we're going to be able to use this to find kind of the sweet spot for the detector position. We want to be in this plateau where we make sure that we're not missing any backscattered protons at all. And there's also, we're going to be able to do a lot of cool things with being able to have position dependence. We're also digitizing signals. So we're going to do some cold pulse shape analysis as well. So the pixelated signal, pixelated detectors are going to be a big improvement for this. So there's a lot of stuff going on in the field of neutron physics. We hope to have a lot of new results, both on beta correlation parameters and neutron lifetime in the next few years. So hopefully in as few as 5 more years, but maybe more realistically 10, this landscape is going to look very differently. And and I'll totally come back and tell you guys about it. Okay, so this is it.
Okay, thank you very much for that great talk. When you come back and tell us about it, hopefully that'll be in person and not over Zoom. Okay, are there any questions? Feel free to either raise your hand or type a question into the question and answer panel.
And I'm finally going to take a sip.
Okay, you have it. Yeah, just as you're drinking, a question popped up.
So we would love to be able to do everything in GEONT. GEONT doesn't go to low enough proton energies in order to do that interaction with the detector quite right. So we are using GEONT for like transport through the proton trap and tracks to the detector, but then we have to switch to a software called SRIM, S-R-I-M. Oh, which is, I think, from it's developed by physicists in a different field that we don't really interact with, but it has like all the materials interactions at the right energies for us. But for BL3, we're actually doing both Cassiopeia and Giant and, SRIM for that last piece. What is the scale of the expense? Okay. So anyone want to guess what the most expensive part of this apparatus would be? It's not the drawings that are produced by engineering students for $10 an hour. So by far the most expensive part of the experiment is this superconducting magnet.
Of course.
It's both the size of the fact that it's a huge magnet with 3 to 5 Tesla field, but the fact that it has to have the magnetic field turn. So the magnet itself is on the order of $2 to $3 million, and the whole apparatus is about 5. So as far as big experiments go, or as far as important experiments go, it's not actually very expensive. What is different about the spallation neutron source? The total power available. So yeah, that's basically the big thing, more neutrons. And also we were able to petition and get our own dedicated beamline that when we had to, then, we had to raise money to build, but it belongs to us. We don't have to really, the neutron community is not very big. So yes, we compete for beam time on it, but there's few enough of us that we just kind of work it out on our own. So the detector design. So luckily we're not doing a ton of R&D because this pixelated detector technology already is being pioneered by other experiments, but I can tell you what's going into this, for example. Just, it's going to be very technical. But so this is what it looks like assembled. And I'm putting this thing inside the magnet, right? From this direction. So the magnet is at ultra high vacuum because, we have to detect every single proton. So there better not be any residual gas in here. We don't want these protons scattering. So the detector, that part of it is seeing ultra high vacuum. This is very shiny, not just by accident. It's a highly polished electrode of a very specific shape. This is the thing that we bias to 30 kilovolts because we want there to be a very smooth electric field. We don't want there to be any pockets for particles to be trapped in. Then the whole thing inside here has to be cold. So this, you can see this, we're adding these copper rings to cool things via contact. At the same time, these electronics don't want to be cold. So we're doing a lot of simulations, trying to figure out where, how to make sure that this is cold, but this isn't. So, we're experimenting with different ways to bring heat in and blah, blah, blah. Then you have to be able to touch it on the outside. So this is a high voltage break. But then the signals are still, riding on a 30 kilovolt signal. So these are the considerations that come into this design. It's not finished.
You had mentioned designing a cooling system. And
Yeah.
I think I saw quickly on the slide, it was 0.5 Kelvin.
So that's the uncertainty. That's the stability of the temperature that Nav
Okay,
wants.
got it. Yeah, I was trying to see because it was like with helium gas.
Yeah, we don't care about as much for the neutron lifetime because we're just detecting protons, and they more or less will have very similar energy ranges. Whereas for NAB, we want to know the electron energy very well, and the gain of the electronics will fluctuate with the temperature. So we don't want to do that.
Okay, so then you said it was a cryo-free system?
This one maybe not. So because you asked, I will tell you. So originally the plan before I joined the experiment, they were just gonna hook up some liquid nitrogen and circulate it through the whole apparatus, and that's cold enough. But
Okay.
it introduces microphonics, and there's a prototype that we saw, like, some serious effects in from liquid nitrogen. So we decided to do flow cold helium gas instead, because it's not going to have a phase transition. It's much easier to buy parts for it because it's a gas instead of a cryogenic liquid. So we have this, heat exchanger that it'll pass through to get cool. It sits on a cryo cooler. There's two, one for the top detector, one for the bottom detector. Yeah.
Do you have any vibrations to worry about from the cryo cooler?
Yes. And the lines to the detectors are like, over 10 feet of transfer line, which is, springy. So also, it's not the biggest vibration in the experiment.
Okay, got it. Are there any more questions?
Unfortunately, every time I give this talk and there are questions, I then incorporate the answers into those questions.
Got
and
it.
then talk.
Very nice. I always have to wait a little because as soon as I think there are no more questions, then another question pops up into the question and answer.
Sure.
Okay. I do not see any more questions. Thank you very much for giving such a great talk. That this is not my field, but I found it to be very exciting and understandable.
Good.
In fact, regarding the price of the superconducting magnets, so I study superconductivity and we have these low temperature systems in my lab. So I'm always talking to my students about the cost of these instruments.
Yeah, this student broke quite a few, multi-$100 sensors.
Yeah, it kind of is what it is. It happens.
Yeah.
Okay, thanks for your time, especially given that you started the talk at 6 o'clock your time.
I'm pretty
appreciate
hungry.
your energy. Yeah, that's right. Dinner time.
Thank you, and I hope to see you guys in person in a few years.
And then if you have any questions for our speaker, again, feel free, as always, to email the speaker or even email me if there are any questions that you would like me to pass along.
Yep.
Okay, thanks everyone, and goodbye.
Good night.
Thanks, Nadia.
Bye, Kyle.
Bye.